Hello, and thanks for using TickBoo. In this video, I'm revisiting part 5 of what is a very difficult proof question coming from the New South Wales HSC Extension 2 curriculum. I got sent this question about a month ago from a student, and they were struggling with part 4 and part 5. And back then, I was able to create some videos to work through how you would approach part 1, 2, 3, and 4. But I got stuck on part 5. It just eluded me in terms of how to tackle this question. So I sent out a call to my network to see if there was anyone out there who had any ideas. And I did get a whole bunch of people contact me and give me their thoughts. And firstly, I should say thank you to all those people for your help. There were plenty of good ideas of how to try and tackle this. In the end, a few people mentioned to me something called the Stolz-Cesaro theorem, and that is ultimately what has proven to be useful in tackling this question. So as I work through the solution, you'll see that we're essentially applying that theorem. There's one person in particular I definitely need to thank. They provided me a lot of detailed guidance on how to work through this question. In fact, the solution you're about to see, it's their solution, it's not mine. I can't really lay any claim to it. There's no way I could have worked it out myself. Now, they've requested to maintain their anonymity, so I'll respect that wish. I won't actually say who this person is, but I really do want to say thank you for all the help and guidance. There's just no way we'd be able to tackle this problem without that guidance. Now, to revisit what the question is, part 5 says that it is given that the limit as n approaches infinity of x1 plus x2 all the way up to xn divided by n to the 2/3. We're told that limit exists and it's equal to a positive real number c, and we're asked to show that c is equal to the cubed root of 9 on 2. So to start, we'll just write that out. We'll write what we're being asked to prove. So prove that the limit as n goes to infinity of x1 plus x2 up to xn on n to the 2/3 is equal to the cubed root of 9 divided by 2. Now the first thing we can do to start tackling this is just to break up this ratio into its numerator and denominator. So we'll let an equal x1 plus x2 up to xn, the numerator, and we'll let bn equal the denominator, n to the 2/3. And the Stoltz-Cesaro theorem that I mentioned states that if the limit as n goes to infinity of an minus 1 divided by bn minus 1, if that limit exists, then its value will be equal to the limit as n goes to infinity of an on bn. So you can see how this could be helpful. We're concerned with the limit of an on bn, but if we can find this alternative limit and we can work out its value, then using this equality, we've indirectly found the limit that we care about. This theorem, you may hear it being referred to as the Discrete Lahopitas theorem. And Lahopitas theorem's something that was in the curriculum when I was studying 4 unit. It's about finding the limit of a ratio of two functions where you can find their derivatives, the ratio of the derivatives, and it's very similar. It's like an indirect way of finding a limit, and this is the discrete case because we're not really dealing with continuous functions. My understanding is Lahopitas rule is no longer in the curriculum, so it would be a bit of a stretch for a HSC student to be expected to kind of take Lahopitas rule and almost invent the discrete version. Because my understanding is Stoltz-Cesaro is definitely not taught in the HSC curriculum. So whilst this technique is what I'm going to work through to show the solution, my assumption is that there must still be an alternative way that only relies on what's in the curriculum. If the If the people who wrote this question happen to stumble upon this video and want to share what they had in mind when they wrote this question, I'd love for them to get in touch and kind of outline what I can only presume must be a simpler approach than what I'm about to work through. Looking back at the question, it's only really worth 2 marks, which when you think about that in the context of an exam, and you look at the amount of work I'm about to go through to apply this theorem, it just doesn't line up. There must be another way, but it just hasn't jumped out at me yet, or anybody else who I've sought help from. But fundamentally, to apply this theorem, the limit of the an minus 1 on bn minus 1, it has to exist. And also bn has to be monotone and divergent. So in this case, bn would always be increasing and it diverges to infinity, so that would be okay. So the next requirement is that this limit actually exists, and I'll talk a little bit more about that as we work through. But step 1 is to go, okay, well, what is an minus 1? And what is bn minus 1? So in our case, an minus 1 would be equal to an, so x1 plus x2 all the way up to xn, but I'll write the last 2 items, you'll see why that's useful, and then minus an minus 1, so minus x1 plus x2 plus just going up to n minus 1. And so when you write it like this, you can see that these bits cancel, so you just get left with xn. And then bn minus 1 is equal to n to the 2/3 minus n minus 1 to the 2/3. So bringing that together, what we can get is an minus 1 on bn minus 1 is equal to xn on n to the 2/3 minus n minus 1 to the 2/3. And it's at this point we do our first kind of little moment of creativity where we multiply the top and bottom by n minus 1 to the power of 1/3. So we haven't changed anything here. We're just multiplying by the same thing, but we'll see later that this is helpful in getting us to where we need to get to. So now what we can say is that the limit as n goes to infinity of an minus 1 on bn minus 1, that limit is equal to the limit as n goes to infinity of xn n minus 1 to the 3rd on n minus 1 to the 3rd n to the 2/3 minus n minus 1 to the 2/3. So that's what we're dealing with. If we can find this limit, then we can apply Stolz-Cesaro to conclude that whatever that limit is will be the same as the limit we care about. So, now what do we do? The way we can break this up is to think about the numerator and denominator separately. So, step 1, we can think about what is the limit as n goes to infinity of xn n minus 1 to the power of 1/3. And what I'm going to do is I'm going to assume that that is equal to k, where k is some positive number. So what we're doing is we're assuming that this limit exists, and then we're going to continue on from there. And so the key word there is that we're going to assume, but really for this solution to be rigorous, we actually need to prove that this limit exists and that it's positive. So what I'll do is I'll actually tackle that in another video, because that in itself is quite a detailed set of steps, and this video is already going to be long enough with all the working involved. So I'm going to do this in a separate video. So what we'll do is, for now, we'll take it as given that the limit does exist, and so we will have this an minus 1 on bn minus 1. The limit will exist, and it will involve this k, and I'll in a separate video work through the steps to show that. So given that, the next thing to think about will be this denominator and what the limit of the denominator is. So I might turn over and we'll just write out what we're dealing with. So we're dealing with n minus 1 to the third times n to the 2/3 minus n minus 1 to the 2/3. So what we need to do is simplify this and then work out the limit. So step 1 would just be to expand. So we'll get n minus 1 to the third, n to the 2/3 minus n minus 1 to the third, n minus 1 to the 2/3. So what I'll do is I'll write this n to the 2/3 as n on n to the third times n minus 1 to the third. And we can see here that this third and 2/3 will add up to 1. So this really just becomes minus n minus 1. So now I can write that as n minus 1 on n all to the power of a third minus n plus 1, which is n 1 minus 1 on n to the third minus n plus 1. Now at this point we can focus on this 1 minus 1 on n all to the third, and we can use what's called the binomial expansion to rewrite that in a form that's going to make it easier to get the limit. So the generic form of the binomial expansion, which is something you would learn in the 3-unit curriculum, so 4-unit students would also be expected to know it. It's 1 plus x to the power of n is equal to the sum from r is equal to 0 to n of ncr x to the r. And noting that ncr can be written as n factorial r factorial n minus r factorial. So what we can do is we can expand this. What we'll get is just working through all the values of r, you'll get NC0 x to the 0 plus NC1 x to the 1 plus NC2 x to the 2 and so on. So kind of expanding this out, you'll get n factorial on 0 factorial n minus 0 factorial x to the 0 plus n factorial on 1 factorial n minus 1 factorial x to the 1 plus n factorial on 2 factorial n minus 2 factorial x to the 2, and then you'd keep going. So this first term would just simplify to 1 plus n factorial on n minus 1 factorial would simplify to n, so you get plus nx, and here you get n minus 1 on 2 x squared and so on. So seeing this expansion, we can now use this to say 1 minus 1 on n to the third is equal to, and wherever we see x we can write negative 1 on n, and wherever we see n we can write a third. So we get 1 plus a third times negative 1 on n plus a half times a third times a third minus 1, which would be negative 2 on 3 times negative 1 on n all squared plus, and you keep going. So there you get, that's equal to 1 minus 1 on 3n. These 2's would cancel, so you get minus 1 on 9n squared, and you probably get another minus, and you keep going. And you keep getting fractions that have higher and higher orders of n in the denominator. So what we can then do is insert this back up into what we were dealing with. So we can say n 1 minus 1 on n to the third minus n plus 1 is equal to n times 1 minus 1 on 3n minus 1 on 9n squared minus and so on minus n plus 1, which would equal n minus 1 on 3 minus 1 on 9n minus and so on minus n plus 1. This n will cancel with this n. The 1 minus the third would become 2/3 minus 1 on 9n minus and so on. A whole bunch of things with higher powers of n in their denominator. So from there, if I just turn over, what we can therefore say is that the limit as n goes to infinity of what we were concerned with, so n minus 1 to the third, n to the 2/3 minus n minus 1 to the 2/3, the limit of that is actually equal to the limit as n goes to infinity of 2/3 minus 1 on 9n minus and so on, where all of these extra terms will just have a higher order of n in their denominator. So we can see that for all of this, because we've got powers of n in the denominator, as n goes to infinity, they'll all go to 0. Go to 0. Which means what we're left with is just the 2/3. So now if we go back to the original limit that we're trying to work with here, the limit as n goes to infinity of x1 plus x2 all the way up to xn on n to the 2/3, we've now simplified that to simply be, first of all, k for the numerator, what we assume to be k, divided by what we've just worked out, this 2/3. So the problem then, we can reverse that. So we get 3 on 2k. That is what we're trying to work out now. So if we can find k, then we've solved this problem and we've got the limit. And hopefully k turns out to be a value that gets us to what we're ultimately trying to work to. So now what we need to do is find k. And to do that, we're going to kind of start again with a new application of the Stolz-Cesaro theorem. So what we're going to do is we're going to start with a new an and bn and see if we can choose those such that we'll be able to work out k. So let's let an equal x1 squared plus x2 squared plus all the way up to xn squared, which happens to be 1 over xn plus 1, because this whole question began with the definition of xn plus 1 as 1 over this, this series here. And we'll let bn equal to n to the power of a third. And now what we'll do is we'll just work through similar steps. So we'll go, well, what's an minus 1? And using a similar technique to before, we'll get x1 squared plus x2 squared plus xn minus 1 squared plus xn squared minus, same thing but only going up to xn minus 1. So they'll cancel and you get left with xn squared. And then bn minus 1 will be n to the third minus n minus 1 to the third. So what we can do now, this an minus 1 is fairly simple. So let's see if we can simplify the bn minus 1. And what we can do is we can let p equal this first term n to the third. And we'll let q equal this second term, n minus 1 to the third. And we can use the expansion, or the difference of two cubes. So p cubed minus q cubed, we know kind of simplifies to p minus q, p squared plus p cubed plus q squared. So now we'll just insert our p and q into this. So p cubed would be n to the third cubed, which will just leave us with n, minus n minus 1 to the third cubed, which would leave us with n minus 1, equals n to the third minus n minus 1 to the third times n to the 2/3 plus n to the third, n minus 1 to the third, plus n minus 1 to the 2/3. This will just simplify to 1. We'll get n minus n plus 1. And so we can rearrange for this bit here. What we'll get is n to the third minus n minus 1 to the third is equal to 1 divided by this. We bring this over, so we'll get n to the 2/3 plus n to the third, n minus 1 to the third, plus n minus 1 to the 2/3. So we've used this difference of two cubes to kind of cleverly get a new way of writing what we're dealing with, being this. So what we can therefore say is, in terms of what we're dealing with now, an minus 1 on bn minus bn minus 1 will be equal to the xn squared divided by 1 over something, which means you end up just timesing n to the 2/3 plus n to the third, n minus 1 to the third, plus n minus 1 to the 2/3. So that's what we're dealing with. So the question is, can we simplify this? And kind of like what we did before, it can be helpful to multiply the top and bottom by something. In this case, it'll be by n minus 1 to the 2/3. That's going to help us simplify this. So what we'll get is xn squared times n minus 1 to the 2/3 times, and I'll bring this denominator in, so we'll get n to the 2/3 on n minus 1 to the 2/3, which is really just n on n minus 1 to the 2/3, plus n to the third times this n minus 1 to the third divided by n minus 1 to the 2/3. We'll just leave an n minus 1 to the third in the denominator, so we'll get n on n minus 1 to the third, and then these two will just simplify to 1. So that then can simplify to xn n minus 1 to the third all squared times, and I'll write this as r squared plus r plus 1, where in this case r is equal to n on n minus 1 to the power of a third. So that just lets us write it in a bit more of a simple way. So what I'll do is I'll turn over, and what we can say now is that the limit as n goes to infinity of an minus 1 on bn minus bn minus 1, that limit for this new instance of Stolz-Cesaro will be the limit as n goes to infinity of xn n minus 1 to the third squared times the limit as n goes to infinity of r squared plus r plus 1, remembering that r is equal to n on n minus 1 to the third. So now, in terms of simplifying this, you may remember, right back at the beginning, we assumed that the limit as n goes to infinity of xn, n minus 1 to the third is equal to k. So here what we're dealing with is k squared times. Now as n goes to infinity, r would go to infinity on infinity, which is 1. 1 to the third was still 1. So we'll get 1 squared plus 1 plus 1. So this will simply come down to 3k squared. So that's a good start. We've kind of got our first limit into terms of k. Now what we can focus on is just an on bn. Because if we can get that simplified such that its limit is also in the form of k, then we can set them equal under Stolz-Cesaro and hopefully solve for k. So in our case, an on bn, you may remember an can be thought of as 1 on xn plus 1. And bn is just n to the third, so dividing by n to the third is the same as multiplying by 1 over n to the third. So an on bn in this case is 1 on xn plus 1 n to the third. So the limit as n goes to infinity of an on bn is equal to the limit as n goes to infinity of 1 on xn plus 1 n to the third. Now remember, going back to our definition of k, that the limit as n goes to infinity of xn n minus 1 to the third is equal to k. We've assumed that it's equal to k. Now if I just come in and wherever I see n, I put n plus 1, so we just go the next step in this sequence, what we'd get is the limit as n goes to infinity of x n plus 1 times n plus 1 minus 1, or n to the third, and it will have the same limit because we're going to infinity, so that's also going to be equal to k. So see, this is the same as this, so what we can say is the limit as n goes to infinity of an on bn is equal to 1 on k. So now we've got that in the form of k as well. So what we can say is that by Stoltz-Cesaro, the 3k squared is equal to the 1 on k, because this limit up here will be equal to this limit. So that therefore 3k squared is equal to 1 on k. So if we kind of bring the k up and the 3 down, we'll get k cubed is equal to 1 on 3. So k is equal to 1 on 3 to the third. And now, remember that this whole problem got reduced to the point where if we can find k, we've got our solution. So we've just found k, so now we can draw our conclusion. The limit as n goes to infinity of x1 plus x2 plus all the way up to xn on n to the 2/3 is equal to 3 on 2 times k. So 3 on 2 times 1 on 3 to the third, which will equal the 3 divided by the 3 to the third will get us 3 to the 2/3 on 2. So that's really the cubed root of 3 squared, or the cubed root of 9 on 2. And that is what we were being asked to show. So we've got our solution. That is what we're required to show. And we've effectively done it by doing 2 applications of the Stoltz-Cesaro theorem. So looking back, it's quite a lot of work there. And as I mentioned before, given this was only worth 2 marks, you really have to ask yourself, is this what the question writers had in mind? And I don't think it was. So I'm really interested to find out if ever one day they happen to stumble across this video, I'd love to find out what was in their head when they wrote this question and what they thought students would do to get these marks. Yeah, ultimately quite a bit of work to do, plenty of opportunities to make mistakes, and also quite a bit of creativity required. I mean, once you even just get past working out that this is the technique to use, there's a few moments like here where we multiply top and bottom by the same thing. This binomial expansion, it might not be obvious to use that. Taking the difference of cubes to help simplify this. I don't think that would naturally jump out to a lot of people. Yeah, plenty of places where we have to have our creativity. So again, another reason why I think a lot of people would not be able to get this. And you also remember, I've made an assumption that we then need to prove. So there's actually more work to go. This question isn't really finished in that sense. For convenience, I've just made this assumption so that I could focus on the task at hand. But actually, if you wanted to get all the marks here, you'd have to go about going through all the steps to prove that this limit exists in the first place. And so that's something I'm going to do separately in a separate video. But yeah, it just adds more to the point that this is a very difficult question for the marks that were up for grabs. But despite that, hopefully you've been able to follow through all these steps, and it's all kind of made sense to you at each point. So I'm very happy to now be able to have a solution to this and be able to share it. It really was quite the journey to get to here. But hopefully you have found this helpful. And tick boom.